Hello everyone, I hope you all are doing well. This side Priya Bhatia. And in this specific video, we will be talking about PCA. Okay, this is, a discussion of dimensionality reduction technique. So let me just give you a brief overview of what is that all about. And then we will start our actual session where I'll talk about the, mathematical intuition behind this algorithm. First of all, people usually you will observe interchangeably use the two terms in ML called as feature selection and dimensionality reduction. These two terms are very different. Please try to understand the difference between these two for the very first part, and then maybe we will deep dive into that algorithm per se. See, if let's say I'm saying that you are having a data set and it is composed of 100 features available with us, and you are trying to apply a few techniques. For example, you are trying to create a correlation coefficient heat map, and you are trying to check that whether the two features are highly correlated or not, and if yes, you're trying to remove any one of them. So if you're trying to take the subset of the given features that you have, for example, out of 100 you're trying to select maybe 20, 30 features after doing various techniques that we have for feature selection. That is something that is a part of a separate category in EDA, I would say, where we are selecting our important features available with us, and whatever features we feel doesn't makes much significance in terms of prediction per se, we are just removing them. Okay. Another term which I am saying here is dimensionality reduction. Today's focus is on that, where what we will try to do is we will not use those given features. We will try to take the important information, or our model will try to capture the important information available in all those 100 features. And we are saying that let's try to create a new features altogether, right? Maybe of dimensions 3, 4, 5, 7, 10, depending upon the scenario, depending upon how many number of features are available with us, depending upon what is the optimal number of components of the features which is required, which is giving us almost 90% or 95% of the information which is already given by 100 features. So major purpose of this session is to understand that if let's say I will be having multiple features, that is something which we call as multiple dimensions. That is something which is a curse for my model. That's why you will heard this term curse of dimensionality. You can read about this, you can read a research paper about this. The simple meaning is that if we will be having so many features available in our data, in that particular scenario, it will not improve the accuracy, or you can say efficiency of our model, but it will make it down. So our purpose is that our model should not get confused. At the same time, it will be able to access the important information from a given data. And how can we do that? That is where the concept of this dimensionality reduction techniques come into picture. And PCA is one of them. Principal component analysis is one of them, which is very widely used in lot of real-time projects, in lot of industry projects. And it's very, very important for you to understand that what is the mathematical intuition behind this algorithm, followed by what is the hands-on implementation for the same. So what we will do is we will try to separate our talk into two categories. This specific video, we will be focusing on the maths behind that. I will try to showcase you with one example, and there will be a second part of this video which I'll release after few days, in which I will try to showcase you the implementation of whatever learnings you will gain here. The main prerequisite to understand the upcoming implementation part is to understand this video. Otherwise, you will not able to get the idea, because our focus is not to just implement the stuffs, but also to understand the maths behind that. So in this video, let's try to understand the maths behind PCA, followed by then we will do the implementation of the same. Please do let me know in the comment section whether you will be able to understand that or not. It will be a maths heavy, required the concepts of eigenvalues, eigenvectors, which is a part of a linear algebra. So it would be great if you have that understanding. If you don't have, please try to refer lectures of Gilbert Strang. It's very widely famous as well, and you can refer that. At least I like that most. So you can just refer that videos. It will be really helpful for you. So now let's deep dive into the mathematical intuition of PCA, principal component analysis, right? So I hope this particular part is pretty much clear, that this is a technique which is basically helping me to reduce the number of dimensions. For example, in this
particular picture, you can see that we have an original data space, which is of 3 dimensions, right? You can see maybe X, Y, Z. 3 dimensions are there. And what we will do is we will try to apply some technology, some method as PCA, which is nothing but indicating a principal component analysis, which is basically helping me to reduce these dimensions, 3-dimensional space, to 2 dimensions, PC1 and PC2. So you can clearly see that this is what we have. This is what 2 dimensions we have composed of PC1 and PC2, right? Now, whenever we are talking about these components, PC1 and PC2, the question will be that how basically we will be able to get that component, right? Now, just make sure that these PC1 and PC2 are different features itself, which is basically we will evaluate by applying some sort of maths. But just make sure that these components of PC1 and PC2, where we are trying to convert a 3-dimensional space or 3D data to a 2D data. So this contains the important information of the 3D data, right? So all the features, all the important features, values, it will extract, information it will extract, our model of PCA, and will try to give us a 2D space where almost all the information will be there, which is given by that 3 dimensions. Same thing will be applicable for, let's say, we will be having 50-dimensional space and I want to reduce it to maybe 2-dimensional. So we can do that by looking into the vector that, okay, we will be having 2 components, PC1 and PC2, which contains maximum information which this 50 dimensions feature values is giving to us. So when we are saying dimensions, always remember this thing. I think in the previous sessions also I have talked about this term. Dimensions, literal meaning is features only. Always remember. Okay? I am trying to convey the same thing here when I'm saying dimensions of the features. Means we are trying to reduce that feature. And one important thing, many people just believe that they will be same only. This is not a feature selection technique. Otherwise, in a feature selection, it usually happens. We try to remove few features and we do have similar features at the end. It's just that we're trying to take a subset of those features. It's entirely different concept today which we are discussing. Here, we are trying to create a new set of features altogether. We are trying to create a new set of features altogether. So if someone will ask you that what is the difference between feature selection technique versus the difference between dimensionality reduction technique. Dimensionality reduction technique. I hope you can clearly explain now after this session. So when we are saying feature selection, it means that we are trying to take the subset of the features, right? We will be having some original data. Let's say that original data contains 100 data points, 100 features that we have. Maybe we are trying to take out of them 50, 40, 30 by applying some techniques. For example, if you remember, correlation heat map is one of the way which we have understood in our previous discussions, which is basically helping me to select the important features. So this is where we will be able to get the subset of the given features that we have. Always remember. Okay? But when we are talking about dimensionality reduction technique, just make sure here we are applying the algorithm in such a way that we will be able to get a new set of features altogether, with lesser dimensions, right? That is why it is called as dimensionality reduction, with lesser dimensions. How we will be able to achieve that? For that, we have seen the technique of, we are looking into the technique of PCA. So this is the major difference, but people usually believe that these two are the same things, and you will observe people are interchangeably using these words. But there's a lot of difference between these two things. So I think in future you will never ever get confused between these two terminologies, right? Now let's move ahead and let's try to deep dive into PCA in the more aspect, that how basically it is giving me the components of PC1 and PC2 mentioned in the image, right? First of all, always remember when I'm saying, let's say, two components, one is PC1, another one is PC2, principal component 1, principal component 2. PC1 always stores the maximum information of the original data features. It will always store the maximum information. Then PC2 will be having a lesser information than PC1, lesser info than PC1. Let me just move it above. But more info than PC3. So what is the meaning of this? Please try to understand PC3. PC3. That this is how the trend will go. PC1 will be having a highest information, then PC2, then PC3, then PC4, depending upon how many principal components you are trying to create. So this is the trend in terms of capturing the important information from original data. Important info from the original data. Always remember. Okay. So with the help of capturing important information from the original data, PC1 will be having a maximum information, PC2 will be having a second highest, PC3 will be having a third highest, and so on. So this is how basically the trend will be forming up. Now, the next important part which we have to understand here is that, okay, PC1 is there, PC2 is there. Always remember they both are also perpendicular to each other. Perpendicular to each other. All the components that we have, whether it be PC1, PC2, PC3, PC4, depending upon how many number of components we have, the important property is all these PCs will be perpendicular to each other. For example, if let's say I'm saying, this is my PC1, okay? This is my PC1. So my PC2 will be like this, just perpendicular. If I will be having PC3, in that case, it will be taking a third direction, which is perpendicular to both PC1 and PC2. So I hope you will be able to get my point. Now, let's move ahead to the next important aspect, that is the mathematical idea that how we will be able to extract the important information out of the given data, right? For that, I'll take a very simple illustration, okay? And we'll try to showcase you with the help of this. So here, you can see that what I have done is, I have tried to import important packages in order to demonstrate you the concept. Please make sure these are the steps which are required in order to create the components of PC1 and PC2. So if you will be able to understand each and every step, it will be really easy task, right? So what we are doing is, we are trying to import the packages NumPy and Pandas. By the way, it is not a hands-on implementation. This is just to illustrate you how the principal components will be formed. I thought that rather than writing the stuff and writing the steps, let me show you, because when we see the visualization, when we see the things, we will be able to understand in a much better manner, right? So here you will be able to see what I have done is, I have manually tried to create one array with the help of NumPy. I hope you all know with the help of NumPy is nothing but it's a 2D array, 3D, 4D, whatever we want to convey, right? It basically used to store the arrays itself and will be able to do the faster computation internally. So now we have tried to create a 2D array here where you can see 6 data points are there. Values are 3, 7, -4, -6, 1, -1, 7, 8, -4, -1, and -3, -7. So this array we have created now. What we are doing is, we are trying to create a data frame of that array, because you all know that whatever functions we have, whatever computations we can do on top of this data itself. So what we are doing is, we are trying to create a separate column by the name of x1 and x2. So here you can see we have a data which is available with us. It's a 2D array, and we have a columns name which we have assigned as x1 and x2. And this is how our data frame is ready now. Now, if you will be able to see, the very first step in our PCA part is to make sure that we will be having a data in a standard normal form. Now, what is the meaning of standard normal form? Let me try to showcase you. So I have mentioned, right, to check whether the data is in SNF or not. Now here you can see, as our data is in a SNF, we are skipping that step to convert our data to a standard normal form. See how basically I am saying that it's in a standard normal form. What is the meaning of SNF? You all know, right? Any particular data is in the form of a standard normal form if it contains mean as 0 and standard deviation as 1. I hope you all know. Now, it's a very small data, right? I have just few data points available with me here, just 6. So what you can do is maybe you can just try to add the x1 values and try to take the average of that. See, 3, -4, 1 and 7. So what I will do is I'll try to add the numbers which is given to me in the form of positive entities, and then I'll try to add the numbers which are in the negative entities. So here you can see 7 plus 1 is 8, 8 plus 3 is 11. And if you will try to see the negative numbers, -4, -4, -3. So -8 minus 3 is again -11. So plus 11 minus 11 cancel out with each other. We will be able to get the answer as 0. Same thing will go for x2 as well. Check it out. 7 -6 minus 1 is -7. So again 0 will be there. Plus 8 minus 1 minus 7 is -8. So again we will be able to get the answer as 0. So if you can try to similarly evaluate for standard deviation also, you will be able to get an idea that mean is 0 and standard deviation is 1. That's why we already have a data in a SNF form. If it is not there, then how can we convert? I hope you already aware about the concept of scaling. We can directly from sklearn import from pre-processing package standard scalar, and we can convert that. Anyhow, in terms of in the future sessions when we will do the hands-on implementation, I will showcase you that concept as well. No need to worry. Another way via which you can easily evaluate the same stuff is by saying data frame dot describe function, because you all know the describe function will help me to give the descriptive stats, right? So let me try to use like this. We are calling the function. So here you can see, right? Our mean is approximately equals to 0, right? But here standard deviation is having value which is 4.472136, which is not 1. Okay, so maybe what we can do is we can convert. So this is the hands-on file. From there we can maybe try to convert our data into a standard scalar form. This is how basically we can do. So let me try to check it out again. So what we can do is maybe we can try to take the pre-processing package standard scalar. I think this thing I've done a lot many times in the EDA part, so I'm not explaining it in a very lot detail, but if you want, you can just prefer the previous videos of supervised learning where I have demonstrated you the EDA task. Same thing I'm doing here. I'm just calling this standard scalar form, which is basically helping me to convert my entire data with the mean value 0, STD as 1. I thought STD is also 1, but it is showcasing me some different values, so let's try to make it 1, right? So we are calling this function, then we are calling fit underscore transform method. Everything, by the way, I have explained in my previous sessions that why it is fit and transform, what is the literal meaning of that. If there is anyone who forget the concept, you have a access of previous videos, please go and check it out. Now here we will be having data frame, right? So now let me try to check whether we will be able to get a standard scalar form data. Again, let's try to see the description. Describe function we will call. Let's see now. Okay, it's an ND array. So maybe what we can do is, again, we can try to convert this into a data frame, right? That would be a great idea. So we can take this data scaled and maybe we can try to convert it. Before that, let's try to see the type of this data scaled so that we will be make sure that it's not in a data frame. You can see it's an ND array, but describe function only works in data frame. So what we can do is we can try to convert again back to a data frame. So we can take data scaled again. Columns will remain x1, x2. Let's do that. And let's try to again recheck the description. And let's see what we are getting now. Now it is good, right? So mean is approximately equals to 0 because it's an exponential of -17, approximately 0. And STD is approximately equals to 1. I think it makes sense now. Okay. Now let's move ahead. So now we have data frame, right? Next target is to get the correlation matrix. So first step till so far we have seen in our journey of getting that PCA components is to first of all make sure that our data is scaled, right? Our data is in a standard scalar form. What is the reason behind that? I hope I I have talked about the same reason again and again multiple times in the last videos also. We don't want our model to be biased towards any one feature just by looking into the values. For example, let's say we will be having two features available in my data. One is population, one is age. Now I don't want that my components will be more biased towards population because it is having a higher scale value as comparable to the age. That's why it's very, very important. In the very first go, check it out. Is your data contains mean as 0, STD as 1 or not? If not, please convert that as shown in the given illustration. Okay. Now second step is to evaluate the covariance matrix of the given data frame that you have. Now before we will try to see how basically we will be able to evaluate this covariance matrix, the important question is that what is the significance of covariance? And I think you also have heard something called as correlation. Correlation. Maximum number of times interviewers usually ask that what is the difference between covariance versus correlation. So the question is how basically you will be able to examine or how will you able to explain the concept behind covariance versus correlation. See, both are providing us the similar conceptual idea. We will be having either the covariance value as positive or negative or 0. Okay. Positive indicates that if let's say you will be having two features x and y, or maybe if you will be having two features, let's say f1 and f2. So if you are increasing one feature, other feature is also increasing. If you are decreasing one feature, other feature is also decreasing. Means somehow they are positively correlated. They are having a positive covariance value. Negative means that they will be having f1 and f2. When f1 is increasing, f2 is decreasing. When f1 is decreasing, f2 is increasing. That is the literal meaning of negative covariance. When you are saying 0, it means that they are not at all in a relationship with each other. Means they are independent. Those features are not depending upon each other. So this is the meaning of covariance. Now, covariance value will be having some scaled value, right? Scaled value, right? So either it will be some positive, there is no as such specific range is there. But when we're talking about this correlation, it is a specific range from -1 to +1. So it is not dependent on any of the unit. It is not a scaled value, right? It's just that if let's say you will be having a negative correlation, or you will be having a 0 correlation, or you can be having a positive +1 correlation, right? Negative again indicates the same thing, right? It is if it is very, very close to that -1, it indicates the similar factor that, okay, basically it is trying to convey us the strength of a given relationship, right? Not providing us accurate value, right? If you want to look for an accurate value, you will always go for covariance. If you want to look for the strength, that whether they are positively correlated, whether they are negatively correlated, or whether they are not having any correlation, it will be always 0. So in terms of understanding, both are similar. Negative means that one is increasing, another one is decreasing. Positive means both are increasing or decreasing. 0 means no relation at all. But their units are entirely different. One is basically used to showcase the strength. Another one is usually showcase you the exact values, right? So what we try to do is, we try to create in a second step the covariance matrix. Now there are multiple ways to create that. Those who are already aware, maybe they can easily able to understand this part. So we want to find out the covariance matrix, not correlation, I should say covariance. Covariance matrix, right? Covariance matrix between two features that we have x1 and x2. So here if you will be able to see, what we are doing is we are trying to take from data frame x1 value, store it in a C1, x2 value, store it in a C2. Now one way is to directly evaluate the covariance matrix is to call, in the NumPy we have a function of COV. We can directly call that, and that function will be able to give us a matrix. So if I'll just directly run this, you will be able to see, you will be able to get a covariance matrix in a wonderful manner. Another way could be where you can just take the transpose of a given matrix into that matrix itself, divided by the value of n-1. N indicates the number of data points that you have. So this is the another formula via which you will be able to evaluate the covariance matrix in a very wonderful manner. So what you can do is data frame transpose. This @ symbol indicates the correlation, the matrix multiplication simply. So in NumPy or in Python implementation, when we want to do the matrix multiplication, we usually represent it by the @ symbol divided by n minus 1. So n indicates the number of features we have. We do have 6 features, if you can see, right? So if I'll just show you also the shape of the data, maybe here only we can look into this data frame dot shape. So if you will just check it out, we will be having 6 values and 2 columns. So number of records that we have, -1 is 5. So manually we have entered that. So if you will just run this, you will be able to observe both of the answers are same only. It's just that in the below we have a data frame type, in the above case we have a array type. That's it. Anyhow we can convert it, right, at any point of time. Another way could be where you can just do the summation and multiplication of C1 and C2 divided by the n minus 1. So anyhow you will be able to observe, so it is giving you the number of this 1.06, because anyhow we are not looking for a same correlation covariance value, right? I don't want x1 and x1 covariance value. I don't want x2 and x2 covariance value. What I'm looking for is x1 and x2 or x2 or x1. These are always same, always remember, right? Cumulative property is there. So always remember, we are looking for x1 x2 or x2 x1, which is this value is what we are definitely looking for. So there are 3 different approaches, but the main focus is to evaluate that covariance matrix, which is definitely coming up similar only in all these 3 ways. It really depends on you. Whatever way you want, you can do that. Now let's move to the third step in the evaluation of PCA. Third step is to evaluate the eigenvalues and eigenvectors. Now, why is that so? See, you have a covariance matrix, which is basically representing to us that how the 2 columns are, having a correlation. And if yes, if they are correlated, what is the exact scale-up values? That is what we have. Now, with the help of which we will be able to get an idea that what is the eigenvalue, what is the eigenvector, with the help of this linealg dot EIG function. Now this linealg in the NumPy we have for the linear algebra functions. Maybe you can refer the documentation if you want to go beyond that, what are the functions we have for the linear algebra in this NumPy part. But this linealg, the full form is linear algebra. This particular package contains multiple functions specific for linear algebra itself, which you can explore. Now, because I'm looking for eigenvalues and eigenvectors for that covariance matrix, I'll call this EIG function, which is basically giving me 2 things. One is the eigenvalue, another one is the eigenvector for the same covariance matrix we have. Now, if you will just run this particular part, you will be able to get an idea that these are the eigenvalues we have and these are the eigenvectors we have. Now, with the help of this eigenvalues and eigenvectors, you will be able to create a principal components. How? Let's try to understand. See, always remember, whichsoever eigenvalue is the highest eigenvalue, you have to take that specific eigenvector to create PC1, because highest eigenvalue indicates the strength of the highest information. And if you remember, I told you that when we are trying to create the principal components, PC1 will be the highest one, then followed by PC2, then PC3, PC4. So always remember, if let's say here so we just have 2 features, in future maybe we are dealing with 50 features. So we will be having 50 eigenvalues, we will be having 50 eigenvectors. So when you are trying to create PC1, PC1 will be the one which is having a highest eigenvalue. Corresponding to that, you will take the eigenvector. For example, let me show you what I'm trying to convey here. You can see here, highest eigenvalue is the 0th value 2.2606017, right? So what I will do is, these are the eigenvectors which I have, right? So either I will be having 0th row or I will be having first 0th column or first column. So what I'm looking forward is all the rows followed by, let's say I'm saying 0th value. So what I will be able to get is, I will be able to get this specific value 0.071 and 0.071, because I am saying consider all the rows, give me the 0th column. Similarly, I can get the first column as well. Now, this is the data frame that we have. finally, right? The question is how we will be able to get the very first eigen principal component. See, zeroth value indicates a highest eigen value. So what I will take is, I will take this zeroth one as the eigenvector. So what I will do is, I will try to do the matrix multiplication of a given data frame with that zeroth column value, because this is having a highest eigenvalue. So I will take this number and will try to do the matrix multiplication, and then I will be able to achieve a PC1. So this indicates my first principal component, which contains the maximum information of my original data. So if, let's say, you want to convert your 2D data to 1D, it's done. Now you have the very first component, it's done. Means it contains the maximum information of your two-dimensional feature set that you have. But let's say you are saying that, I want to create the second principal component as well. I want to see how it looks like. So maybe you can take the second eigenvalue wala vector, and then in that case, again, you can see. So here now you will be having entirely different feature set, because if you remember, my actual data frame looks like this, where I will be having entirely different data points that we have, right? Entirely different data points. But my new feature set contains two principal components, where first principal component contains the highest information because it is given highest eigenvalue. And then if, let's say, I want to go for second PC2, it contains smaller information as comparable to PC1. So if, let's say, someone is saying that I don't want to use the 2D features, I just want to use the 1D feature, but I want the maximum information to be available, in that case, they can directly go for PC1 and they can train their model in terms of PC1 itself. I usually don't consider this as an unsupervised technique. I usually say it's a part of a EDA only, where you are trying to do the data analysis and you're trying to see that whether the dimensions are very huge or not. If yes, then you're trying to apply these kind of techniques to reduce the dimensions, right? But anyhow, usually people, you will see in multiple platforms, they're calling it as a category of unsupervised, because again, training data outcome value is not available. So it's fine, but definitely, as per my picture, I believe it should be a part of EDA. And whenever you are having a data, you should consider in the initial steps itself that whether there is a need to reduce the dimensions or not. Maybe if you are not able to understand at that moment, then maybe you can just go ahead and then when you will see the outcome, the accuracy, then you will go back to the EDA part and just apply this knowledge, okay? So this is how basically we will be able to evaluate the principal components. So in a nutshell, first step is to check whether the data is in a standard normal form or not, to avoid the biasness. Second step is to create a covariance matrix. I have already explained you mathematically also what is the literal meaning of the same. There are three ways which we have seen. One is directly calling the function, another one is directly using the formula, and the last one is again with the help of formula itself. Third thing is to evaluate the eigenvalue and eigenvector. Eigenvalue will be able to provide me the highest strength eigenvector. Once I will be able to get that, with the help of which I will be able to get the PC1 by just doing a matrix multiplication with the actual data frame that I have, and I will be able to achieve the PC1. If I want PC2, definitely I can do. So always remember, if let's say you have 50 dimensions, you can create 50 principal components. But always remember, first principal component will be the one which is having the highest eigenvalue. Correspond to that only by taking that eigenvector and doing a matrix multiplication with the original data that we have. So I hope that until so far, whatever picture I want to convey here, mathematically is pretty much clear to everyone. Also, there can be a one question that, Priya, how we will get to know that which particular principal component is providing us a maximum information, right? Let's say we will be having 50 features available with us. How do we get to know that, how many principal components do we create, right? At any point of time, so that our maximum information will be captured. For this, there will be a concept of, explained variance ratio, which we will cover up in the hands-on implementation part. Also, we will try to discuss the PCA documentation also in the upcoming sessions. So just make sure you will stay tuned, because until so far I have not used this particular direct I would say algorithm to implement the things. In the very first session, I just want to showcase you mathematically how things are working. So that's why, if you will be able to observe here, we are not using any direct function of PCA. But internally, when you're calling PCA, this is the kind of maths is going on. So I think now in future, you will be able to understand that how this PCA is working internally. If anyone is not aware about the eigenvalues and eigenvectors, I would suggest please go refer, I think Gilbert Strang lectures are there on YouTube. Very amazing lectures on eigenvalues and eigenvectors. You can refer that. Then you will be able to understand that what is the purpose of eigenvalues and eigenvectors and how basically we can evaluate that. Here I won't go in deep maths of eigenvalues and eigenvectors. The only reason is the major focus is to showcase you PCA, not to go deep dive into mathematical part. But I would highly suggest, if there is anyone who is not aware about this internal facts of these eigenvalues and eigenvectors and listening these terms for the very first time, please do refer his lectures on any of the resource which you find it preferable. Check it out. And with this, I will see you all very soon.